If you're training a large language model and you want it to go faster, one of the options is to use more GPUs and to parallelize that training so you can get done more quickly. I'm going to talk you through a way to do this that's called distributed data parallel. It involves making a replica of the model on each GPU so you can scale the speed roughly by the number of GPUs that you have. Now, I already have a video that shows how to do this with the transformers library, but I'm going to use the Unsloth library today, which is about 2 times faster than the transformers library, but does come with a few quirks that you need to be aware of. So I'm going to start the video by describing what distributed data parallel is and how it differs from other parallelization algorithms like tensor parallel or model or pipeline parallel. There are pros and cons of each, and you want to use distributed data parallel when your model can fit on a single GPU. That's the short summary. I'll talk about where this is good, how much speed up you get, and then I'll move right into a demo where I show you how to take a script. Maybe it's a notebook you got from Unsloth for a collab, and you convert it into a .py script, which is necessary if you're going to run on multiple GPUs. And then I'll show you the adjustments you need to make to convert from running on one GPU to multiple GPUs. Broadly speaking, there are 3 ways to train models on multiple GPUs. There are combinations of these 2, but there's data parallel, tensor parallel, and pipeline parallel. Data parallel, which we'll focus on today, involves making a copy. Here I've got 2 GPUs, 2 H100s, and the model will be loaded in full. So the weights will be fully loaded on each GPU. And every batch we run, instead of just sending it to one GPU, we'll send it now split into 2 micro batches. So we'll have 4 here on each. And once we forward pass through each of the GPUs, we're going to, at the end of the forward pass, accumulate the gradients, and we will average them out and then back propagate again through these models in order to update them. So basically, we do forward passes in separate GPUs, but we take and combine that information, and we use the combined information to update the weights. So essentially, we keep the GPUs in sync, we keep the model states, the weights in sync as we move through the training. And because we have twice as many GPUs or more, 3, 4, 5, usually powers of 2, you're going to get a speed up that's roughly equivalent to the number of GPUs that you add in. Now, I'll briefly mention 2 of the other types of training, which are tensor parallel and model or pipeline parallel. I do cover those in detail in a video on Fully Sharded Data Parallel, which is a tensor parallel approach. And suffice to say that if possible, you want to use distributed data parallel, but you can only do that if your model fits fully on each GPU. As you can see here, if the model doesn't fit fully on the GPU, you're never going to be able to replicate it off each GPU. In that case, you basically have 2 options. One is to do pipeline parallel, which is actually the default if you set the device map in Transformers or Unsloth to auto. It will, I think actually in Unsloth, you might need to set it to balanced. It will split the first half of the model on one GPU and the second half on the other GPU. But the problem with this training is you will forward pass through this first, and the second GPU is just idle, waiting for information to come from the first half of the model. So you end up with a lot of idleness when you use pipeline or model parallel type approaches, whereas you can just keep the GPUs both purring or whirring, or I'm not sure what the word would be there, stirring. You can keep them all going if you're using data parallel. So pipeline parallel, while it's straightforward and it's actually easy to code, and as just mentioned, you can set device map, I think, to auto in Transformers or to balanced for Unsloth. It is going to be slower because your GPUs are going to be idle while they wait for each other. The most sophisticated approach that you can use for multiple GPU training is tensor parallel. And here it involves taking matrices and splitting them essentially vertically. So you might have one matrix and part of the weights are being held on one GPU and part are being held on another GPU, and you accumulate information between the 2 GPUs like this. Now, this is more complicated mathematically because you need to carefully manage how these matrices are being split, but it does allow you to take a model that is larger than any single GPU and split it onto multiple GPUs. And this would be very common for training very large models because it avoids having idle GPUs because you don't have this passing of weights from one to the other. So you avoid that idleness, but also you can fit models that are larger than any one GPU on its own. Now, in practice, I think in 2025, it should be pretty rare if you're training your own model. It should be pretty rare that it doesn't fit on a single GPU, because you can now rent, say, H200s. If you go, for example, to RunPod, you could rent a B200 with 180 gigabytes. B200 not yet that well supported, but so I would recommend a H200 SXM. That's 141 gigabytes, and you're going to fit nearly any model. If you're trying to train something larger, you really have to ask if that is going to cost too much money when it comes to inference. So I would question in a lot of cases if people are training custom models that don't fit on a single GPU. And so distributed data parallel is becoming even more relevant now, because the GPUs are bigger, so you pretty much can always fit the model on a single GPU, and therefore you can do this distributed data parallel rather than tensor parallel. And for what it's worth, data parallel is a lot cleaner because each model just fits. There is no latency involved with transferring weights between GPUs. There's just a small amount of information at the end of forward propagations when you accumulate gradients, but that's a very small amount of communication compared to the large amount needed in tensor parallel here. So again, if you want to look at fully sharded data parallel and tensor parallel, I should maybe just say fully sharded tensor parallel, or FSDP data parallel. You can check out the video on the fine-tuning channel on FSDP, but for now, I'm going to show you how to use Unsloth with doing distributed data parallel. Now, there are two steps involved here. The first is you want to take some kind of script. So if you go to, say, GitHub and Unsloth, you can find a very large number of scripts. For example, you could take, let's say, this Gemma 4B model. So I've got here some kind of a script that's going to allow me to fine-tune Gemma. It looks like this will also allow you to tune based on images. So you could, for example, download this script here. Just click on download. And if you like, you could even just download it as a .py straight away. So don't even run the conversion yourself. Or you can download it as a Jupyter notebook, the .ipynb like that. And then you could decide to do the conversion yourself, which I'll show you in a moment. And you must do the conversion to .py because you need it in script format, so you can run the script with a library called accelerate, which is going to effectively run the script on multiple accelerators. So that's why you need to have it in the .py format. One other note on Unsloth is that generally Unsloth is going to be twice as fast as transformers, but it's limited to a single device. If you operate in distributed data parallel, you can actually keep the benefits of Unsloth while while scaling up your speed by adding in GPUs. So this is quite a nice feature. Unsloth does not yet support fully sharded data parallel, so that might be on the roadmap, but not something that you can do today. So with that, I'm going to move to show you the adjustments you need to make to a script if you want to run distributed data parallel. And I'm going to do this using notebooks I've made available to those who are members of the advanced fine-tuning repo. You can find out more about it at trellis.com/advanced fine-tuning. And you can either purchase lifetime access to this or to all of the Trellis repos. There are now 7 of them by getting the multi-repo bundle. So I'm in the advanced fine-tuning repo. I'll show you it right here. Within, there are a wide variety of fine-tuning scripts here. There's also a main README that'll help you navigate around the wide variety of scripts that are available. But we're going to work out of the fine-tuning folder and then the Unsloth DDP folder. But I actually want to work on a GPU. I don't want to work locally. So I'm going to start up a GPU and start running some of the scripts. And one of the easiest ways to do that is with this one-click template here from RunPod. I'm going to select 2 GPUs. So you want to run it on maybe 2 A40s like this. And you can see that if you use this one-click template, it's going to install everything. It's going to set my Git username. So I'll be logged into Git already via environment variables I have set here. I'll show you a video. I'll just link it now up above if you want to see how to do this one-click setup. It saves an awful lot of time. Anytime I want to do a fine-tuning, it'll be up and running in a few minutes, as opposed to manually having to set, say, Hugging Face token IDs or GitHub variables. So if I clicked deploy, and I did this earlier, I actually did it on 2 H100s. I can move over to the Jupyter notebook, which should be up and running here. Let me see which tab it is. Yep, this one here. And you can see if you navigate into the workspace folder, the advanced fine-tuning folder will already have been cloned. And we're going to operate out of fine-tune, and then we're going to operate out of Unsloth DDP. And within that, we're going to focus on this README, which provides a full guide on how to run distributed data parallel. Now, the first thing I've already mentioned, it's converting an IPYNB notebook into a Python script. You can either do that by downloading it as a Python script if you're in Jupyter, if you're in Colab or in Kaggle, I think, as well. Or you can run some simple commands. I have this script, notebook to script. You can run notebook to script.py, pass in the path to your IPYNB, and then pass in -o, the output. This is the name of the output file you want to create. And that should be enough to just create a fine-tuning notebook like this one here that we're going to use for distributed data parallel. Now, when you convert the notebook, you should be able to just run it as a py file, and you should do that. You should run it by doing uv run and then pass the file here to check that the file still works in .py format. If it doesn't work in .py format, it's probably not going to work in multi-GPU, and it definitely is better to debug it in single GPU than to try and move to multi-GPU first. Just a few notes on installations. Often, if you're in a notebook, say like this one here, you're going to run the installs at the very start of the notebook. But if you're running a script, you're going to be doing the installs first outside of the script. So what you'll want to do is you want to SSH into the pod, and you want to upgrade pip. I like to install UV. It's a faster package manager, and then install Unsloth on the system. You may also want to install tensorboard if you want to take a look at logs. So that's a tip there. And actually, I'm going to show you how to log in. I'm going to go to my pods, click on the pod, click here on the SSH command, and then I'm going to open up a new terminal. So I'll show you this on screen now, 1 second. Here I've just opened up a terminal, and I've pasted in that SSH command, and I'm going to direct it to my SSH key for runpod, which I've set up and needs to be set in the runpod dashboard. And with that, it should connect into the pod. And if you do ls, you won't see any files, but if you do cd back up one folder, you should see here a number of folders appear, including workspace. And the one we want to move into is workspace. And then we want to move into advanced fine tuning, and then fine tune, and then Unsloth DDP. So now I'm in this same folder that you saw in the Jupyter notebook. Now we can check Unsloth is installed. So you could do uv pip show Unsloth, and Unsloth should be installed there. I'm going to increase my screen size a little bit. So you can see it's a version from August here. And yeah, I was just explaining there how you should do the installs that normally would be done within the Jupyter notebook. So we've done the installs. We've got our training script here, train_ddp.py. And now we need to move to take a look at a few of the modifications that need to be made. And there are a few things that we need to change. The first thing is Unsloth will try and do some compilations that will break the pre-existing builds. Namely, it will try to do some patching of some of the trainers like DPO trainer or ORPO trainer or some other ones. And that's just going to break your run. So it's wise to import torch and then set these environment variables here just to make sure that Unsloth does not do that. So you'll see in train.ddp, I'm importing these variables right here. Now, also, it's helpful to determine whether you are on the main process or on the other GPUs. If I have 2 GPUs, which I do here or more, one of them will be assigned as the main process and the others will be, secondary processes. And you sometimes want to do things only on one GPU. For example, at the end of a run, if you're going to merge the LoRA weights to the main model, you don't want to do that on every GPU. You just want to do it on one GPU. So you're going to assign one of the GPUs for doing that. So it's useful to define a local rank which is just getting from the environment this variable local rank, which should already be set, and also to define the main process, which is the rank 0. And once we have main process defined, what you're going to see is that throughout this script, there'll be places where we do things that only happen on the main process, like print statements. We only want to see once, otherwise it'll print for every GPU. Or if we want to launch tensorboard, we clearly don't want to launch it multiple times. We just want to launch it once. So we're going to make sure it only happens if we're on the main process here. So this is the first set here of updates. The next is we need to pass in the device map. And this is essentially telling each GPU which, we're telling the fast language model here which GPU this is. And the way to do that is with torch.cuda.currentDevice. So there's this helper here that already tells us which device we're on, and we need to pass that into the device map. So you'll see that happening down here when we load up the model. So we're loading the model here, and we're just going to pass in a device map here. Now you could use the local rank. This will work as well, but you can also just pass in torch.cuda.device map like this here. So that should work fine. You can see again, we're using the isMain process because I don't want to print on every single GPU. But let's get back here to the plan and look at some of the other updates. So the other thing we need to do is in the supervised fine-tuning configuration, we need to pass 3 key parameters. The first is for distributed data parallel, we need to set find unused parameters to false. I don't know exactly what this does here, but I know this is a key flag that you want to set. And it's also mentioned in the Unsloth documentation for distributed data parallel. Now, we have some arguments here around gradient checkpointing. Gradient checkpointing is typically set in Unsloth when you either load the model here or when you applied the PEFT. It's common to set gradient checkpointing to Unsloth, which uses a flavor of gradient checkpointing that will save memory. Gradient checkpointing means that as you do forward passes, you don't actually store all of the information. You will recompute it just before the backward pass, so it saves you some VRAM at the cost of extra compute. Typically, you would train with Unsloth here, which saves memory. And typically, in the SFT config, you would use reentrant equals true. This means that you have graphs that accelerate the recomputation of those numbers you have thrown away to save memory, and it's typically favorable to have it turned on. But it's known that it can cause issues with DDP for LoRA with transformers. However, I've been running it true and it has been fine, so perhaps you won't run into those issues. Now, I'm going to come back to talk about this average tokens across devices because there are a number of tied up issues. But first, we should check if we're going to use any logging software that we only have weights and biases true on the main process. And also, I guess if we're not on the main process, we need to disable weights and biases. And if we are on the main process, then we need to log in and initialize. That's what that does. Now, I'm using tensorboard, not weights and biases. So when I start the server, as I showed you in the script, I'm only going to start it if we're on the main process. So back up here, when I start weights and biases, which should be here, you can see I'm only doing it if we're on the main process. So with that done, we actually should be ready. I'll just show you very quickly what the script is doing. I'll walk you through it. So we're importing here from Hugging Face Hub. We're logging in. The token should be set in the environment if you use the one-click template, so it won't ask you to log in. If you didn't set it, then you'll need to pass in a token and log in. That's because we're going to push the model up to Hub. We're going to define the directories for where the weights will go. HF home. I've already talked about how we set the world size, which should be 2, the local rank, define whether it's a main process. And by the way, the reason I set world size is just because it's handy. If I want to set a run name with the number of GPUs, I can now use this world size variable. If you search for it down below, you'll see that I use it here. When I set gradient accumulation, I'll talk about that in a second. And I also use it just to do some logs. The GPU tag is going to be based on the number of GPUs, and that ultimately feeds into the run name here. We do some checks down here. That's not too important, but here you can see again, I'm setting the run name based on world size. Okay. So then we start tensorboard. We pick a model, Quen here. For Quen, you need to decide whether to enable thinking or not, depending on the data you have. I have this flag here for doing a test run. It means that we only run a subset of the rows of data. This is very useful to set to true because you can run your script and it won't take too long to train, and you can tell if there's any issues from start to finish before you decide to do a full run. Max sequence length. This needs to be at least as big as your largest row of data. Of course, we'll take more memory if it's larger. dtype equals none lets Unsloth pick based on GPU whether to use float 16 or bfloat 16, brain float 16. You can quantize if you want. I believe this should work with DDP, but I haven't tried it myself. Then the training hyperparameters. So for rank, we're going to set the adapters. We're not going to actually train the model itself. We'll train a set of adapters. The rank is the size of those adapters. Bigger means more granular. It means it should be able to carry more information. 32 is usually sufficient. LoRA alpha should be the square root of the smallest matrix dimension. I actually have removed those checks. You can check out one of the other Unsloth scripts in the repo if you want to learn more about how to set the value of alpha and how to inspect the model to pick out the size of the matrices and therefore the square root of the size, which should be the value of alpha. Next, we have the per device training batch size. And actually for DDP, we're going to set this to 1. You can set it to more than 1, and you can do that with transformers. You can do it with Unsloth too, but currently there is an issue when using Unsloth with a batch size larger than 1. It involves an issue with what's called view. Unsloth tries to minimize as much as possible copying weights, and so it uses view instead of cloning of weights. But in DDP, this isn't possible because you're not able to modify when there are multiple GPUs involved. You're not able to do any edits that are required. So using view doesn't work. It does work on batch size 1 because it turns out that the way the tensors are handled will allow that view operation to work, I believe. So you can get Unsloth to work currently with a batch size of 1. If you want a larger batch size, you actually need to update the SFT trainer, which I'll show you briefly below. And I think my fix would work, but I would caution a little bit because there's actually another error that I'll get to soon that also needs to be fixed by Hugging Face, which I think is going to be merged soon. And it's just an error in logging, to be clear. It's not an error in the values. So then we set gradient accumulation steps. Typically, I like to have a virtual batch size of 32 and set my gradient accumulation based then on my per device batch size, which affects the memory I use, and also the world size, which is the number of GPUs. So if I have 1 GPU and if I have a per device batch size of 1, that means I'll have 32 gradient accumulation steps. So I'm only going to back propagate every 32 steps. But if I have 4 GPUs, then I'll only have 8 gradient accumulation per GPU because there's going to be a world size of 4. So that means I'll only back prop every 8 times 4, which is still every 32 steps. So I like keeping the virtual batch size constant. That allows you to make apples to apples comparisons. So basically you think about it like increase your batch size until you run out of VRAM on the GPUs, and then just set your gradient accumulation so that your virtual batch size, which is 32 divided by the per device batch size divided by the world size, this will then dynamically set an appropriate level of gradient accumulation. We're going to train for 3 epochs. I think we'll just train with a cosine scheduler. And this is the learning rate, probably fine for about a 1B model. Maybe could be a little bit lower because this is a 4B model. We're going to use the touch rugby dataset. It's quite simply got questions about the game of touch rugby and some answers. Here I set the question column. I set there's also an answer column, which needs to be set to answer. And there's a criteria column. This is actually less relevant because we're not doing any evaluation of the answers, any fancy judging of the answers. We're just going to be running a fine tuning here. If you want to learn more about evaluating the correctness of answers, you can take a look at some of my videos on fine tuning in the fine tuning playlist. But for now, actually, I think all you need here is the A column, answer, and the Q column. I'm not even sure. We may not even need that because there's no evaluation at all. So I think I can just comment that out. Now, optionally, you could load a different evaluation data set. By default, it will use the validation split. I think that's provided in the data set. Let me just see when we load up the data set here. If I search for load data set, here we go. So we're just loading up the data set. And if there is an eval data set, we're setting that as the evaluation data. We're also checking if there's an eval split in the fine-tune in the data set, then we'll use that eval split. And if there's none, then there just is no validation split. So you can configure either a separate data set for validation, or you can use the validation split if it's present. Okay, so we next will format the data set. And I'm saying a lot of things that are in a lot of the other videos, so I'm moving quite quickly here. But we need to set up messages that contain the user question and then the assistant question. And you can see we do need Q column and A column. So actually I need to leave those commented in back up here. The Q column is question, the A column is answer. We're setting up messages with questions and answers. And we're applying the chat template then. And that will give us some formatted text that will combine the question and the answer. And we're ready then to go into training. Here we're just setting up a run name based on the dataset name. And then we're moving on to decide whether to turn on evaluation or not. It'll be on if we have an evaluation dataset. And then we move to the supervised fine-tuning configuration, which sets the batch sizes for training and eval, the gradient accumulation steps, the epochs, the logging parameters, the data type that we're going to use, float16 or brain float16. We're going to use tensorboard. We're going to report, we're going to save the model outputs to outputs. And we're going to use a cosine scheduler, which I said. And these are the custom params that need to be set for DDP. Now, actually, I think if you don't set these, it'll probably still work because they'll be set behind the scenes. But this one here, you do need to pass for sure. Next, we've got the run name being updated. So in fact, some of the setting of the run name right here is probably not all that important. We can check if the run name is passed in anywhere else. But I think this probably is superfluous. Yeah, I think we can probably just clean that up here. And I don't think the current timestamp is being used either. You see, this is a much simplified version of a script that I previously have shown. So we're ready then to, do one more thing, which is we have a question and an answer, and we typically only want to train on the loss for the answer. So we want the model to get good on the answer, not to get good on producing the question. So we usually only want to train on what comes after the assistant tag. And the assistant tag depends on the model. We're using Quen right here. So we'll detect which template we need to use for then marking off the losses that we want to train on. And then we will actually print that out. So we'll train on responses only, passing in the instruction and the response tag. And if we're on the main process, we'll print out what that looks like in the unmasked and masked format. And we'll see that in a little bit. Next, we're going to print out the GPU stats. We'll print out some stats here about the rank and the world size. Not essential you do that. Then we'll run training, run the memory stats again. And now if we're on the main process and if we set this to true, or if we set the next one to true, we can either save the model in merged format or we can push it to hub in merged format. And we only want to do that if it's the main process. So going back to the README here, we are almost ready to run, but before we run in multi-GPU mode, what you could decide to do is just run the script as is. And let me do that. So if I go back to here and I say, let's see, I'm just going to move back to. And what I'm going to do is I'm going to run without using anything multi-GPU. So I'm just going to do a standard run, which actually you could have done before the modifications too, but afterwards you can still run it to check everything's working. So I'm going to run that. Now, before we start, I'm just going to remove, be careful with rm-r, I'm going to remove my logs directory just so it's empty and we'll see some fresh runs. And then then I think we're going to be ready to just run this in standard format with UV run without doing multi-GPU. And for that, it looks like I have a bug. And the bug is that I'm missing a comment here. So I'll save that. And now we can run training. So you'll see here, there's just one GPU available when I run like this. And it's going to load Unsloth. We should not see duplicate logs because we're just running on one GPU. And the training should proceed. So loading the checkpoints. It's showing here the model. This is what the model is composed of, the architecture. Applying the LoRA adapters. Here you can see the data set. We've got 193 in train and 22 in validation. Here it's showing a sample of data, question, and then an answer. And we have an issue with run name here. So I need to check this. Ooh. So just copy. Sorry, go back over. Search here. And you can see run name is undefined. And that's because I need to check. It's because I cleaned up the script. Maybe that was, yeah, that was probably a mistake actually making that cleanup. Not to worry. We can go back to the repo itself because I haven't pushed these changes. And let's just search for run name. And sorry, my screen is quite small here. So if we go to run name, yeah, that was a mistake to remove that. I thought I was simplifying. I clearly was not. So I need to put that back in. We'll put it in just before the do eval, which is here. All right. And yeah, we'll just overwrite and hopefully try again. So these are the things to be aware of if you make some quick changes. Should reload the shards and apply the LoRA adapters, define the run name, hopefully properly this time, and run. And I recommend you do this. It's worth actually running without using accelerate or torch run, just to check everything's working. Okay, so now we are training. And you can see we have one data parallel GPU. The batch size per device is 2. So actually in this case here, gradient accumulation steps are 32. And the total batch size is 64. So actually it's setting a larger batch size than expected. So I'm going to check my batch size here in the script. And batch size should be right up here at the top of the script. Yeah, per device train batch size is 1. So I need to check world size. Yeah, and the reason this is happening is so you have 32. World size should be 1. So everything is training fine here. Batch size per device is 2. So it seems to be receiving the wrong value for per device batch size, which I'm not entirely sure why that's the case. So, yeah, I'm not entirely sure why that's the case, but everything is running fine. If we just copy this run pod address up here, there's a quick way to see the logs just by putting 6006, and we should see one run here. We can see the losses coming down on eval, which is good, and we can see the grad norm is it's reasonably stable. Maybe our learning rate is a little bit high there, to be honest, and the training loss here is coming down, which is good as well. So our kind of test here has worked, with the exception of that batch size issue there, which we'll come back to. Next, to run with multiple GPU, what you're going to do is run accelerate and then config. And by the way, just notice here that this run took about 1 minute 25, and that was using one GPU, so we'd expect to get faster if we use more. So here we're going to select accelerated config as a way to configure multi-GPU training. We're going to configure multiple GPUs. Don't be confused here by number of GPUs. This is number of nodes, so it's actually just one. Should distributed operations be checked? Just go with defaults here for no to Torch Dynamo, no to Deep Speed and FSDP, no to Megatron. And then we'll say we're going to use 2 GPUs for training. We're going to use all of them, press enter. We won't use NUMA, and we'll use BrainFloat 16. So that saves our configuration, which is going to be here. And you can copy paste that if you want, because next you're going to want to run this. So when you go down to running the script, we're going to do accelerate launch, and then we're going to pass in the path to the config file. You can pass debug if you like, and then you need to pass the path to that tuning script. Now, before that, I like to remove the Unsloth compiled cache. Unsloth will typically compile a cache right here, wherever you ran the scripts. And sometimes it can cause conflicts, and it's best to remove. You can also run NVIDIA SMI, which allows you to check the status of the GPU. So we'll run all of those. It should have cleared the cache. You can see there's nothing loaded. It's just 1 megabyte out of 81 gigabytes. We have 2 GPUs available, and hopefully everything should run smoothly now with this distributed data parallel. Notice we've duplicate logs. That's correct, because it's logging on each GPU. And everything is printing out well. We're prepping the data sets. You can see 193 train rows. And here we do have an error. And I need to check that everything is okay here. It looks to me like we didn't pass the correct device. So it's having an issue here. torch.cuda.current device. That seems to be the issue. I know, because I've seen it before. Don't think I suddenly figured that out. Yeah, that device map should be correct. I'm not sure why it isn't. Device map. Torch.cuda. And what I'm going to do is just swap this in here in case there was an issue coming from Torch. And I am just checking. The order of import of Torch can matter as well. Import Torch. You want to import Unsloth after Torch. Anything you change to Torch, if you change it after Unsloth is loaded, is not going to have an effect. Let's just see here if we can get by this. And you can see training is running here fine. And I don't think that's to say using that approach is wrong, but I am just going to put that in for now because I have that working right now. So you can use the device map of the local rank. So I'll adjust that here just because it's exactly what I have got working. But I think it should be possible to get torch.cuda.current device working. If you wanted to debug that, I would recommend printing this out. You would want to just print it out somewhere above and check that it does print the correct rank. I know from the forums that this probably should work as well. But for now, yeah, this one here I recommend. And it should just set the local rank. And looks like the training is completed successfully. So everything looks good here. About 1:27 for this. And we can go across and check our logs in tensorboard. And actually, this is a different tensorboard I used from earlier. This is the one I want to use. And you can see there are 2 logs here right now. And our training loss, in this case here, is looking good. It's looking consistent in the 2 runs. I do want to mention something about that, though, in a moment. And you can see the eval loss here. Some little differences here, but we know the batch sizes were not quite equivalent. So possibly some reason for that there. Now, what I want to do is, just for comparison, I want to go back and run accelerate config. And I want to set it this time to run with just 1 GPU. So we should have everything running on this machine, no distributed training, say no to all of these defaults. And we're only going to use GPU 0. We will pick everything else the same, BrainFloat 16. And now we're going to run again. But this time only 1 GPU should be available. And so we'll have a comparison that we can show on tensorboard. This time hopefully both with a batch size that's the same and comparable. So you'll notice that here the batch size is local batch size of 1, 16 gradient accumulation and 2 GPUs. Whereas here, it's going to be, well, we won't see it yet. Here we go. It's 1 by 32 because we've only 1 GPU. So it's using gradient accumulation of 32 on that single GPU. And this should give us a more apples to apples comparison in the 2 runs. And actually, I suspect you will see training loss will be off by a factor of 2 when we run this for reasons I'll describe. That will be fixed probably if you're watching this after September 2025. Fixed in the transformers library. But everything here should be giving correct gradients though, so your model should be training correctly in either case. So here now, we're also going to see that this run is going to be quite a bit slower. And the reason it's going to be slower is because we're using just 1 GPU instead of 2. Previously, it looked like the 2 runs were the same speed, but that's just because we used a much higher batch size in the first run, which will help. If you've got extra compute, using a larger batch size will always help. Obviously, you wouldn't move to multi-GPU until you've tried to speed up the single GPU as much as possible. So you will always try and increase your batch size until you find that your training slows down or you run out of VRAM, and only then do you consider multiple GPUs. So yeah, in this case here, probably we've got some headroom to increase our batch size before we go to multi-GPU. And of course, to some degree, if you force yourself to use a batch size of 1, particularly with a short sequence length, you're not going to be fully using the GPUs. So there's a sense in which it doesn't make sense to do what I'm showing, which is to set the batch size to a low value like just 1. Ideally, you want to max this out as something higher. But with Unsloth, until that view issue is fixed, it won't be possible to go above 1 unless you do a custom patch, which I'll show you in a moment. So this training is almost over. It's about a factor of 2 slower because we're using 1 GPU instead of 2. So it should finish off momentarily now, and we can check in tensorboard here. If we look at these 2 runs, which are more apples to apples, we should see in training loss the value of 1 GPU and 2 GPU. And actually our training loss here looks pretty good. So I'm pleased about that. And the grad norm looks very good as well. So everything looks consistent here. And yeah, our eval loss looks consistent as well. So this is excellent. I just want to double check my scripts. So if I go over here, we're using the SFT config, the SFT trainer. I want to show you some of the issues that have been going around just to explain, because I was finding that my training loss was different with 2 GPUs compared to 1 GPU. And that issue there seems to be somewhat resolved. There's a specific pull request open. It's this one here. So if I go to the pull request around the issue with losses, I can find what it says. It's still waiting to be closed in, but yeah, there is an issue around GPUs, the number of GPUs affecting the loss normalization in trainer. So I'll put a link to this in the description. Just keep an eye out if you see the same thing. I believe it's going to be merged quite soon. I saw some tests going on it earlier. So probably if you're looking at this in the future and you still have issues with the training loss being different when you do 1 GPU or 2 or multiple GPUs, then maybe take a look at that issue to see if something else has gone wrong, but hopefully it'll be fixed. And right here, I'm not seeing any issues at present. My training loss is looking good and consistent, whether I use 1 GPU or multiple GPUs. Now, if you do want to use a batch size larger than 1, what you need to do is, first of all, set your batch size larger than 1, which I can do up here. And let's go back and do accelerate config. And we'll go back to using 2 GPUs here. So if I use this machine and I do multi-GPU, accept all the defaults here, and then use 2 GPUs, and accept the defaults and BF16. If you try and run now, you are likely going to run into an issue with Unsloth, and that's because of that view. It's not cloning, it's trying to view, and this poses an issue when it's trying to view tensors when there are multiple GPUs involved. And the way that you can address this is by custom writing, subclassing the SFT trainer, which I can show you a patch for. But the problem with that patch is, well, I think the patch works fine, but you should double check it yourself to ensure that you're not getting any issues. Yeah, you can see here that you're getting an Unsloth issue, and it's to do with the fact that it's trying to modify a view function in place. Unsloth uses view to save memory and operations. So you can try and apply a custom patch. I'll show you the custom patch here. What it would require is basically subclassing SFT trainer like this. So instead of running view, it instead is going to use clone. So you can see here it's cloning, but you need to be really careful what this custom loss is doing. There is a well-known issue at this point, which surfaced last year, to do with gradient accumulation, where when you're combining the losses from different steps, you need to make sure that you weigh them according to the number of valid tokens adjusted for padding. So you ignore padding. You can't just average and do a mean across them if they have different lengths and different padding. And the same thing applies across multiple GPUs. When you combine across multiple GPUs, you don't want to just weigh each GPU with a weight of 1. You need to adjust it according to the number of unpadded tokens. So you need to be careful when you try to adjust this here. If you put in a patch, I can just show you very quickly what it looks like to put in a patch. I'm going to go down to the SFT trainer, and here I'm going to paste in this safe SFT trainer, which requires importing the accelerator. And with that, we can try to rerun, and we'll see what we get. What would give some confidence is if we see the losses are similar as for the 1 GPU case. And if they're not, then it just indicates that this patch probably needs another look. So we've downloaded checkpoint shards. The LoRA adapter should be applied. Notice that we're training just a few percent of the parameters, 1.6%. And okay. Yeah, so this is true. If you do want to subclass, you need to set average. You basically need to cancel this computation across devices that correctly factors in padding, and you need to do so by commenting in this line here, which is average tokens across devices. And I do mention that in the README. So if you check the README here, It'll advise, do I mention it in the README? Yeah, I mention it up here. When you set these variables, this actually needs to be set to false. So maybe I should highlight that further down here. So you need to set this in SFT config. So let's take a look at how that's progressing. Looks good, at least in terms of errors. But the way the loss is being described here, I think is going to give rise to that factor of 2 issue. Yeah. So when we go back and take a look at tensorboard, we should see a new run appear here. And you'll see the loss here is larger, and it's not even larger by a consistent amount in this case. And that may be just due to how we are reporting. And we may be reporting, for example, the loss on the single GPU as opposed to the aggregate loss here. So yeah, I don't really recommend doing these kind of patches like I've done. We can check the eval loss to see if, it looks like roughly it's tracking, but it's not quite on track here. You would expect to have some effects because of using different batch sizes. So for example, when we look at this run, you can see it's 2 by 8 by 2. So you do have different splitting of the data, and that can result in differences. But yeah, I would be kind of careful before using this because of the differences involved. And so what I recommend is stick to the basic. Don't subclass as I've done here. I would just leave this as it was with the original SFT trainer. So here, just leave in what was there and try and train on batch size of 1. Typically, the reason you'll have to move to multiple GPUs is because you can't do large batch sizes anyway, either because you've long sequence length or you have a very large model. So hopefully you'll still get a benefit from multiplying across multiple GPUs. But ideally, it would be nice to be able to do batch size larger than 1. I'm going to set it back to 1 so it doesn't break for those of you who use this. So I set this here to 1. And with that, and also with just commenting out that line about setting to false, it will default to true, and it will be able to do the correct aggregation across GPUs. So that was DDP with Unsloth. You can see there are still 1 or 2 things that hopefully will be ironed out by the time you're watching this on the transformers front. This should hopefully be merged. And also there is an issue posted around fixing the view issue with Unsloth. It is really nice though if you can do multi-GPU with Unsloth, because you do get that 2x speed up from using Unsloth versus transformers. Plus then you can scale out how fast you're training by adding more GPUs. As I said at the start, you can get the scripts on trellis.com/advanced fine tuning. You can buy lifetime access to this repo, or you can buy access to all of the Trellis repos. There's 7 of them there if you are interested. In the meantime, I'll put some of the key links below in the description. Also, want to give a shout out. In some of these GitHub issues, I got quite a lot of help. There were 2 different contributors. Let me just find them here. Here we go on the multi-GPU training. Particularly, shout out to Urban Sprinter and Rakshith as well. Thanks very much for the help. I'll put a link to this in the description as well. And that's it. Let me know of any questions in the description. Cheers, or in the comments rather. Cheers, folks.